Now go.
This is lesson 3, 3 complex numbers in Algebra 2, page 172. We are going to learn a whole new set of numbers today. Since about 7th or 8th grade, we learned about rational numbers, and then we learned about irrational numbers. And so, and we learned that group was called the set of real numbers. Okay. Well, there's an even bigger set of numbers out there called the complex numbers. Okay. And we do not talk about the complex numbers until you get into upper level math because they are complex. So it takes a fair amount of understanding of other ones to get here. What do complex numbers compile of? They compile of a real number and an imaginary number. This is called the real number. And this is called the imaginary number. So when you add the two together, you get a complex number. Now some people call them the real part and the imaginary part. That is the form that we use is a plus bi. Okay. Now if the a is gone, it's just called a pure imaginary number. And obviously if this is gone, it's just called a real number. If you put the two together, that's when we get a complex number. It all started when we tried to solve an equation like this. And we took the square root of both sides and the square root of x squared and the square root of a -4. What happened was we got x equals, and we said this was plus or minus, because you remember you got a plus and negative. But we didn't know how to do the square root of a -4 because there's no two numbers that we can take times each other gets a negative, or no number times itself that we can get a -4. Now you can say, oh wait a minute, what about a -2? No, a -2 times -2 is a +4. So complex numbers were created to solve equations like this. So what we did was we came up with an idea. Hey, we're going to define. You want me to move that a little bit?
No, it's fine.
Okay. We're going to define this letter called I, and it's going to equal the square root of a -1. Okay. That's what. So so we poke an I out here. That's how I say it. We poke an I out. So this is the square root of I. Excuse me. This is I times the square root of 4. And so our answer is x equals plus or minus 2i, because the square root of 4 is 2. So everything is based on the concept that I equals the square root of a -1. And so we can put I in there. Everybody knows that we're dealing with a set of complex numbers. Okay? So I is the first one, right? Okay? Yeah. So I'm just going to say I equals I. And I, remember, I stands for the square root of -1. You need to know that. All right. I squared is the square root of -1 times the square root of -1. So that equals what? Anytime you take something and you square it, you get -1. Correct? Mm-hmm. I mean, you get what's underneath the square root, right? We good? Mm-hmm. Okay. I cubed is a -1. I cubed is I times I squared. You agree? Because 2 plus 1 is 3, right? Mm-hmm. So I is I times I squared is times a -1 equals a -I. So I cubed is a -1. Now I'm doing this for a reason. Don't think I'm just playing here. You got it? So now I to the 4th power is I squared times I squared, right? Because 2 plus 2 is 4. So that means it's a -1 times a -1 equals 1. Okay? Now, what I'm about to tell you is that from here on out, I to the 5th, I to the 6th, I to the 7th, it just starts repeating these. So I to the 5th is I to the 6th is a -1, I to the 7th is a I to the 8th is 1, I to the 9th is I to the 10th is a -1, I to the 11th is a I to the 12th is 1. You'll notice that any I to a multiple of 4 is 1, correct? So let me tell you a quick way of knowing this.
But it's also a multiple of 2.
Well, watch. It is, but since it's rotating in 4. It's rotating every 4, right?
Yeah.
So what I'm going to tell you is that if your number, your exponent, like I to the 75th, if that number 75 is divisible by 4, in other words, my remainder is 0. My remainder is 0. We get this, 1. Okay? Now, just going up, this is remainder 1. This is remainder 2. And this is remainder 3. Let me show you how that works. So can I move I to the 75 down here? I didn't realize I could do this down here. Okay, so I'm going to take 75 and I'm going to divide by what number? 4. Always 4, because it rotates in 4. So we go 1, 4 is 3, bring down the 5, correct?
Mm-hmm.
Right, 35 is 8.
Yep.
That's 32, and we get a remainder of 3, right? This is the big part. We don't care what this is. That doesn't make a difference. It's only the remainder. If you look at it, remainder is 3. This is I to the 3rd. That's how you simplify it. Okay?
Oh.
Okay? Because it can be simplified. All these can be simplified. Right?
And it'll never be a remainder more than 3.
No, because we're dividing by 4.
Yeah.
Okay? So tell me, what is I to the 231st? I to the 231st. Oh, I'm sorry.
Yeah, it's the same.
Okay, what'd you get?
I cubed.
It really is?
Yeah.
Okay. That is not your final answer. I thought I put it up here, but I didn't. What is I to the 3rd?
Negative I.
And this is a negative. I apologize. I should have picked one. I didn't even do
So
this one.
when you write it,
You write a negative I.
I.
Yeah, I thought I did up there. I think I might have said it. Maybe we can look at the video. But your answer will be I, a negative 1, a negative I, or 1. These are the 4 answers that you'll get anytime. So if I did, I better do another one. I can't believe let's say that I did I to the 18th. 18 divided by 4 is 4 with a remainder of 2. So my answer is a negative 1. And so you're going to have one of these 4 answers anytime you have I to a power. Okay, now we very seldom do this a lot. Okay? We very seldom do this a lot. What we normally do is simplify using I. So that's our next set of directions is how do we simplify using a negative underneath a radical? Now it's always a square root, isn't it? Okay? It's always a square root, right? Okay, so let me give you an example. We'll start out, I did one over here, but if I did something like this, what is the square root of a negative 121? Okay? Well, the negative square root of 121 is we poke an I out first. So we take I out, and then we take it times square root of 121. So what is the square root of 121? 11. So my answer is 11I. Does that make sense?
Yep.
So any perfect square root, we're just going to have that number times I, right? However, if you get something like this, a negative, or the square root of a negative 8, Okay, now remember, the negative has to be underneath the square root, not outside. So now I poke an I out, right?
Yeah.
And I have the square root of 4 times the square root of 2. So I have the square root of 4 is 2, 2i square root of 2. So we go back to using our radicals, our simplifying of radicals, but we're poking an I out also. Yes?
We only do that when the negative is, right? Or
Or if it's underneath, yes.
underneath.
Yeah, now if you're gonna,
I don't need it.
if you're gonna multiply 2 together, you gotta poke an I out before you ever do this, yep?
Why does the I not go in front of the 2? On 2.
Okay, that's a great, yeah, I'm glad you brought that up. The I does not go in, it's like a variable. It goes after the number, and it goes before the radical, because if we put it after the radical, sometimes it looks like it's underneath the radical, so we started moving it to the front. That's exactly why that works. Great question, all right? Okay, what happens if we have the square root of a negative 6 times the square root of a negative 15? Okay? All right, so before you ever multiply these, you must poke an I out. Because what happens when you multiply these two together? A negative times a negative is a, and the reader would never know that there was a negative underneath the radical. Okay? So what we have to do is we poke an I out before we ever start. All right? Now, I rearrange them, and you probably won't show this on your paper, but I rearrange them like this. And I put the i's together, so I multiply. And the commutative property of multiplication says I can do it in any order I want, correct?
Yes.
So I times I is I squared times the square root of 15 times 6 is 90. Is that correct?
Yep.
Okay. All right. So what is I squared? Well, I squared is a negative 1. Right? And you should know that right off the top of your head. I squared is a negative 1. Correct? Thank you. Thank you.
Yeah.
Did you want to come up and teach?
Teach? No, what are you learning about?
Complex numbers.
No, I don't want to teach.
All right. Thank you.
Yeah.
What goes into 90 that has a perfect square root?
No.
9 and 10. All right. So we're going to take a negative 1 times the square root of 9 times the square root of 10. So here's a case where we don't have I, but we end up having a negative 1, because now we have a negative 3 square root of 10. If you hadn't done that, if you hadn't poked the i's out, you would have gotten 3 square root of 10, which would be false, because it's not 3 square root of 10. Does everybody understand that?
Yes.
So when you multiply i's together, for example, if I take 3i times a negative 5i, watch what happens.
How'd you get a negative 3?
Negative 1 times the square root of 9 is negative 3.
Okay.
Correct?
Yeah.
Okay. We good for this one then? Okay, ready? Okay. So now we can use community property and associative properties, and I can put 3 times a negative 5, which is a negative 15i squared. Now watch what happens. What is I squared?
Negative.
Negative 1. And you should always remember that. These two you should always know. Okay, these two you might have to memorize, but these two you should always know. So I'm going to take a negative 15 then, times the negative 1, which is a positive 15.
Yep.
Right? Okay. Now, would you do this one for me, please? Would you do square root of a negative 20 times the square root of a negative 12, please? Okay, how many of you multiplied, or poked an eye out and then multiplied the two together? All right, so you went I times the square root of 20 times I times the square root of 12, and so I get I squared times the square root of 240, correct? So that would be a negative 1 times,
I did 16 and 15.
does 16 go into 2? Okay, how many?
16 and 15.
16 and 15, so it's the square root of 16 times the square root of 15. So I'm getting negative 4 square root of 15. You got that? All right, very good. Another way you could have done it was you could have taken and broken this down as the square root of 4 times square root of 5, square root of 4 times square root of 3, and done it that way. Doesn't matter. Okay, that actually is smaller numbers, but with the use of a calculator, we can handle those things pretty well. Okay? Well, on page 174, if you look at page 174, they show you a Venn diagram of real numbers and imaginaries put together, and the set real numbers. So real numbers makes up part of it, and then complex numbers make up the other part, the whole part of it, and imaginary numbers are on the side, and there's a nice Venn diagram to do that. Okay? So, complex numbers, if two complex, listen very carefully, if two complex numbers are equal, then their reals are equal and their imaginaries are equal. So let me give you an example of what I'm talking about. Let's say that if we have 3x minus 5 plus quantity y minus 3i equals 7 plus 6i. Okay, now look here. This looks really confusing. Okay, it looks like a bunch of a long equation, and you're going, wow, this is kind of interesting, not sure how I'm going to solve that. Well, let me show you what happens. Okay, this is the real part. How do I know? Because this number is times that. So this is the imaginary part. Do you get that?
Yeah.
Okay.
Yeah.
This is the real part, and this is the imaginary part. All right? So I just told you that if two of them are equal, the reals have to be equal, and the imaginaries have to be equal. Correct? All right. So I want to take the real and set it equal to 7. And I want to take the imaginary, y minus 3, and set it equal to 6. Now you'll notice that I can drop the i's because the i's are the same, right?
Okay.
So I can solve for x and y and know the values of them. So I'm going to add 5 to both sides, which is 12, and I'm going to divide by 3. I get x equals 4. So x equals 4 and y equals 9. Do you understand it? So if I set an imaginary number equal to an imaginary number, I can get equals. I can get the real numbers to be equal and the imaginary to be equal. Okay? All right. Any questions so far? Well, did you know if you can add real numbers together, do you think you can add imaginary numbers together? Or
Yeah.
complex numbers together? Yeah.
Yeah.
And if you can subtract real numbers, can you subtract complex? You bet. So here's what happens. The directions will say add or subtract. Correct? All right, so what I do is I'm on number 6. Right?
Yeah.
And I'm going to say 5 plus 6i plus 9 minus 3i. Okay, I have this first complex number minus the second one. Okay, just like when we set them equal, when you're adding or subtracting, we add the reals and we add the complexes. So we use the commutative and associative properties. We change all subtraction to addition, and then we put 5 plus 9 together because there's the reals, and we put the 6i plus a negative 3i's because there's the imaginaries. You see that?
Do we have to put I behind it?
Yes. Yes, because these are i's now. We're not solving for anything. We're simplifying. This will say add or subtract. So now my answer is 14 plus 3i. Because 6i plus a negative 3i is 3i. 6 monkeys plus a negative 3 monkeys is 3 monkeys. Does that make sense?
Yeah.
Now, you can also, if you can add them, you can subtract them. But subtracting is a whole different ballgame. Okay? Because you can't be moving stuff around, you know, like commutative and associative property, that doesn't work. So I can go a negative 3 minus 4i, subtract 5 minus 8i. Okay. So I have two complex numbers subtracted. Now the way I do this is I change all subtraction to addition right off the bat, and then I distribute a -1 into the second one, because you're going to subtract both these numbers. You can't just subtract the first one, you have to subtract both. So what I do is I take a -3 plus a -4i plus a -1. Now once I do that, I can pull the parentheses out. But I cannot pull the parentheses out of this one because I'm going to bring that -1 throughout the quantity. Why? Because I'm subtracting both numbers. So what I'm trying to do is change the sign of subtrahend and follow the rules of addition, right? Same thing I taught you in 7th grade, okay? It's just a little more complex. So now I bring the -1 through, and I have a -5 plus a positive 8i. These two are like, so a -3 plus a -5 is -8, and these two are like, plus 4i. Okay? You see the difference between addition and subtraction?
Yes.
Any questions? Well, what do you think the next operation is that we go to?
Multiplication.
Multiplication. I'm going to do one real quick, and then we'll shut down for the day and save division for tomorrow.
Division?
I feel like that would be very
Division?
Yeah, it's not all that great. All right, multiplication. Remember FOIL?
Yeah. Sadly.
Sadly, well,
Sadly, I remember reverse.
if I have 3 minus 2i times, now notice there's no plus sign in here. On the test, I will give somebody this, and they're so excited about foiling that they'll foil this. I have probably 40% of my kids on the test foil this. And this is addition. Okay, but they're so excited. Oh, I got a complex number times a complex number, I'm gonna foil it. Nope. Alright, so a -4 plus 5i. Alright, so there's your two complex numbers. There's no plus sign between them. There's no subtraction, which means we're multiplying. So I use FOIL. I take 3 times, first change this to plus and negative. 3 times -4 is?
-12.
Alright, outer is 3 times 5i.
So 3 times.
15i. Inner?
Positive 8i.
Positive 8i, and last.
-10.
10i squared. There you go. That last term is a squared. Alright, so let's simplify. You know that these two are like, correct?
Yep.
Alright, so I can add them together. I get 23i, but this is a -10 times a -1 because I squared is a -1, right?
Mm-hmm.
So now I have a -12 plus 23i.
Wait, -12.
Yep. 3 times -4 is
Oh.
12. And then that's a positive 10, right?
Mm-hmm.
These two are like, correct?
Yep.
So I have a -2 plus 23i. Folks, when you write your answer, you should have the real part first and the imaginary part second. When we get to division, that is quite a problem. Okay? It doesn't always come out nice and neat. Alrighty? So whenever we multiply, we put the real number first and the imaginary second. Alright, so your assignment. Yes, it's back to the old school, guys. Okay, because this is a new concept. Yes, would you write it down? It's page 176, page 176, page 176, 18 through 60. And I apologize for so many of them, but it's very important that we see all kinds of these problems.
18 through
60. 18 through 60.
Oh,
Okay?
sorry.
Alright, 18 through 60. And this is not tomorrow, it's
Oh,
due the
you
next
can't
day.
turn it. I was going to try to
Okay.
show it.
So, go ahead and shove it.